Hi guys, my name is Paul Lemieux. I work at Motiv RC. This video is really just about kind of informing people as to what we do here and how our motors are built. We started business about a year ago, and there's been a little bit of a hype around the company, and I just wanted to, I guess, kind of explain what we do here. I think it's about time that our potential customers know a little bit more about our product and how we go about, getting the product to you, really. So we're going to go over basically a basic motor build here. I have some pre-selected parts because I didn't want this video to be, super long. So, and I'll start off again by, I guess, apologizing for how terrible I am behind the camera, but bear with me if you can. So we're going to build a 17.5 motor, which is it's the most popular seller of ours for sure. First things first, we have a spec sheet here. Basically every motor is built off of one of these sheets. It has a number of different criterias on it, and each thing that we write on it basically has a tolerance that we use, that if it doesn't meet the tolerance and we can't make it meet the tolerance, then it simply doesn't get used. That's just a way for us really to track the quality of product we're sending out, the quality of product we're getting in, and it's nice, with the big inventory, we're able to manipulate quite a few things to make sure that every motor we sell at least falls in the guidelines of what this spec sheet says. So you will receive that with a motor, so when you open the package you'll be able to look at it. It's definitely not a dyno sheet. It's simply something that basically tells you that you're getting a quality product. So we'll start here. We start with the stator. We already assembled the bearing in the nose plate here, and put the nose on the stator. So we start here with just a resistance check, where we check the resistance of the A, B, and C pole. And we're looking for something that's 0.3, 0.4 ohms from highest to lowest. Obviously if they could be perfect across the board, we'd love them all to be, but we set a tolerance around 0.3, 0.4, where if one's a full ohm off, for sure it's not going to make it into your hands. So on this particular 17.5, it's a 21.0 on pole number A, 20.9 on pole number B, and 20.8 on pole number C. That gives us a variance of 0.2 ohms with an average of 20.9. And so we just write it right in on the sheet. And we'll take a rotor here. We have a Gauss meter. This particular rotor is a 1575 and a 1560. So that's a variance of 15 with an average of 1567, we'll call it. Generally the tolerance on the rotors are 20. Alright, so now that we have a rotor and a stator that are within tolerance, we'll start to assemble the motor. This particular motor takes one of the large shims and 3 on the bottom and 3 of the small ones on the bottom. Put a little bit of the grease on the shaft itself, just put a little barrier between the motor shaft and the race of the bearing. And we kind of set the shaft in the bearing there and get a sensor unit. Generally I kind of eyeball the sensor unit to see the spacing from the sensors to the top of the rotor, and we're looking for something that's about a 0.5 millimeter to 1 millimeter of clearance there. That assures that the sensors are going to pick up on the rotor properly. Got the spacing right, so we'll oil the bearing and get her together. We'll start it at about the 45-degree mark for a 17.5. That's normally somewhere around where we want it to be. Generally, a 17.5 coming from us will be set anywhere between 47 and 49 degrees. That's just kind of a good general starting place for pretty much any class. So we're going to fire it up here on our motorizer, and basically that's going to tell us the rest of the information that we need to be able to quality control the rest of the magnet and also the sensor, and be able to give an accurate timing. Alright, so pole number A is at 44 degrees, pole number B is at 45 degrees, and pole number C is at 46 degrees currently. Our tolerance for the sensors are 3 degrees from the highest to the lowest sensor, which is something that we really stress. You know, we feel like all the tolerances that we set are to enable a motor to go together and really have a standard of how it's going to run in your car. So the tolerance on the sensors are 3 degrees from highest to lowest, which is a pretty tight tolerance, because we feel like that's a very important part to a motor running smoothly, efficiently, and not building so much heat. So I turn the timing up a little bit to hopefully get it around 47, 48 degrees. We'll run it again. Alright, here we go. So sensor A is at 47, sensor B is at 48, sensor C is at 49. So we'll call sensor B the 0, sensor C is plus 1 degree, sensor A is minus 1 degree, with a variance of 2 degrees. The asymmetry on the rotor is 1 degree, which means basically a pole of a magnet, the two poles should be exactly 180 degrees apart. And this one happens to be 1 degree out, so it would be 181 and 179, let's say. Our tolerance for this is generally around 4 or 5 degrees. You know, I think basically 6 and below, the rotor still performs well. Anything over that, it's not good. So that's something that we definitely look out for to make sure that our production is good. So you'll see the asymmetry number represented on the rotor, and then the total timing's at 49 degrees right now. So we'll write that in. And then when I was spooling it up here, you know, I'm listening for more bearing noise than is common. I'm listening, I'm feeling for more vibration than I think is common, and that's also something that we take into consideration. So throughout the build, you'll see we have a visual inspection on this side, just the machining of the can that we're kind of checking everything over, the bearings and the alignment. The alignment, we're always looking for the shaft to be able to move freely in its end play. If there's ever some stick there, then I know the bearings aren't aligned, so we have to go and realign the bearing and rebuild the motor. The sensor board is functioning properly. We take a look at the solder joints and the windings to make sure that there's nothing that's loose or that we feel is in danger of shorting out right away when you would receive one. Lastly, we write who built the motor, the date of the motor, and the motor number that it is, and that just allows us to give a reference as to, you know, when the motor was built, who built it, and that's really about it. So at the end of the build here, we've got a spec sheet that basically tells us, you know, that every component of that motor is up to our specifications, and we feel that it's gonna perform well in your car. And then it goes to packaging. Every motor is pretty much done, made to order. So we've got, you know, our packaging that we make here in house as well, all ready to go with the cushions in there, so we know that the motor's being supported inside of here and it's not going to get knocked around too much during shipping. And there you have it. There's a Motiv 17.5 M code, and that's, you know, a lot of what we go through. You know, we just feel like we're putting out a product that we're proud of at a price that's not the cheapest on the market, but definitely not the most either. And yeah, that's it. So I don't really know how to end this, but I think that's a good. That's what we do here. Thank you for watching, and see you at the racetrack.